Good evening, everybody. I sit in my London office and try and connect the dots and write stories about what's happening in the IT world. And over the past year or so, I've picked up that CXL has got these rather fabulous possibilities. But I just get little isolated pictures of what's going on, a little dot here, a little dot there. And then I come to FMS 2022. The breadth and depth of what's happening with CXL is totally amazing. I'm blown away by this. There's so much going on. So it's obvious. We're about to enter a petabyte memory era. This just blows my mind, the idea of having access to a petabyte of memory. And CXL allows us to have this external pool of memory available to servers which themselves are limited by their socket count. And they're having to run compute-intensive and data-intensive applications that are just strangled because there isn't enough memory. And the analogy I have in my mind is that we've all got vehicles, we've all got cars, SUVs and trucks and so on, and we go on the road. And the engines have fuel delivered to the cylinders by fuel injection. But every so often, the gas tank empties, and we have to fall off the road and fill up the petrol. And it takes a long time. It chews up the journey time. If only we had very large gas tanks, then we could just carry on motoring and not have to pull off to the gas station. And that's what CXL does for memory in IT terms. So, how is it actually going to affect applications? Because I just see things in black and white. There are going to be these very large applications with very large data sets and very compute intensive, and they're going to run like greased lightning in a CXL system. But there's bound to be 50 shades of grey in this. So our panel is going to explain those shades of grey to me. And if they could quickly introduce themselves, I'll be grateful.
Sure. I'm Manoj Wadekar. I'm at Meta, looking at our storage and memory infrastructure for our internal private cloud infrastructure.
Yeah, my name is Bernie Wu. I'm the VP of Business Development and Alliances for MemVerge.
I'm Richard Solomon. I'm the odd man out because I'm the hardware guy here. I'm the technical marketing for CXL controller IP at Synopsys.
My name's James Cuff. I'm an independent strategic advisor. I used to be a scientist.
I guess we just get 12 and a half shades of gray. Is that how that works out?
Okay, panel members. How will pooled CXL DRAM affect IO-bound applications needing more memory? What are the points we need to understand? And if we could take it from this end first, so Manoj.
Sure. I think CXL offers a lot of exciting opportunities, and I think as it's going to go through, in our humble opinion, from our use cases, I think it will go through, to your point, different shades of gray, where it really starts offering the memory expansion capability on a native platform, starts locally, make sure that, because the problems are going to be two-phase. One is basically applications that have standard memory, but at the same time, applications that want more memory, in other words, other standard resources, like CPU or anything else. So it can perhaps start from native memory getting expanded, and then slowly move out and see as the capacities increase, as the bandwidth increases, as the capability for debugging and requiring having the insights into how to connect the pooled memory from outside. And then you get into the most complex area of shared memory, where you start sharing the memory. So I think it's going to be a journey now. But the good thing is basically there's an opportunity to decouple this compute from memory, and it allows us to explore this. So I think it's going to be a journey.
And it's a journey that you're going to take at Meta very, very carefully, because you've got thousands and thousands of servers, vast amounts of money inherent in this, and you're going to want to make very careful certain steps as you go forward.
Absolutely, and I think this is something that we see very carefully, and I think there was a question that was asking that, hey, how are the systems going to be ready for this, right? So we look at, as I said in my previous discussion there, for hyperscale, the infrastructure, it's extremely important to build the balanced systems that allow us to have performance as well as the efficiency. And I think having the independent control on the components that offer that is extremely important. Now, CXL offers that independent choice between what memory attach I do versus what compute offers as a memory interconnect. So definitely we look at all the opportunities that allows us to grow performance, because it of course gives me additional bandwidth, but also it allows me to do more efficient design, because I can now have memory that is tuned for my application needs, potentially going for pooling, etc.
Bernie, for the other sorts of enterprises, not quite as large as Meta, what do you think will happen?
I'll make this first comment. I think this is probably the most exciting time in the industry since the advent of the SAN. And initially, when we look at it, yes, as he was mentioning, the initial CXL will be locally attached memory expansion, and then it will move to pooling. And as we make that transition, when I look at it, initially we're going to be addressing memory-bound applications. So applications that were either limited by bandwidth or limited by latency in a local server environment. And then later on we'll be moving to a pooled environment. And I think it'll introduce more flexibility in terms of composability, collaboration, and other kinds of capabilities. But also when I look at this, at a high level, I think everything is memory bound, you know? So it's not just CPU bound. And what I mean by that is there's a whole class of new capabilities. Besides just doing transparent memory tiering, I think what MemVerge is trying to do is introduce new types of memory data services that were just not possible before. So for example, in the area of snapshotting, of memory snapshotting, we can introduce things that improve time, what I call time to value, our run clock execution time. We can introduce improvements to, and these are all transparent, introduce improvements to recovery time objectives, recovery point objectives. So there's a DR aspect to this that I think is critical in a 24/7 world. And then there's the overall TCO reduction that we can accomplish by addressing more efficiently compute nodes that are memory bound.
So it's not simply going to be, hey, Mr. Enterprise, instead of having 500 gigabyte memory servers, you've now got 1 petabyte of memory available, and everything carries on exactly as before. It doesn't. You're going to have a much more complicated infrastructure to manage, and you're going to have software to do that.
Right, yeah. We're going to enrich the application besides just providing transparent memory access, yeah.
Well, and my colleagues have talked a lot about the top level of the system, and I know James is going to talk in a moment about the actual applications that run on top of that. So let me take the sort of shades of gray at the bottom, the very, very low level there.
Are you a bottom feeder?
I'm definitely a bottom feeder, and I've got to give my apologies to Field of Dreams and build on Frank's baseball metaphor before. If you come to CXL, will they build it? And the answer is yes, right? I think certainly we're here at Flash Memory Summit, so I got to throw in about non-volatile memories, but I can say that definitely there are a lot of companies out there that are very excited about building CXL devices, both with volatile DRAM, HBM style memories, and with non-volatile memories. So we're going to really start to see the hardware at the low level enables that system composition that we've all been talking about all day long to actually get to places where we have pools of both volatile and non-volatile memory. And that's going to allow some really cool stuff.
Thank you. So I said earlier that I used to be a scientist. So I have a PhD in molecular biophysics from Oxford, right? And after that, we attempted this thing called annotating the human genome. It turns out that's quite a data-intensive challenge, especially in the late 90s, where the most sophisticated storage systems we had were things called fiber channel and HSG80s, and some of those technologies that have long since gone. I bring this up as a reason for two things. We've been talking a lot, and Charles mentioned this, that CXL from a distance looks like a SAN, right? It's disruptive. And when we were annotating the human genome, it was disruptive because we were able to put lungs on machines, and it was kind of exciting, but it was very operational, right? And so it didn't really disrupt the science. I'm not saying that being able to present a lung helps us somehow miraculously annotate the human genome, but it was an enabling device. Fast forward in my career, I ended up running Harvard's high-performance computing center from scratch, but also within that environment, we had a series of enterprise stranded islands of compute. One of them was a very complicated piece of compute called the Molecular Cellular Biology website. It was a highly available application because if it went down, the faculty were very mad that their vanity pages weren't visible on the World Wide Web. So it could not suffer any outage. And at that point, we took this same storage area network technology. My friend Arvind will chuckle about this. We used this technology called VMware. And we presented this same LUN that we were talking about to this VMware device. And we used this thing called vMotion. And I presented this in front of the Harvard faculty with a window of my vMotion console and another window issuing ICMP pings to the highly available website. And was able to move the website between two computers, from computer A to computer B, and the website didn't go down. That was the killer application, right? And I'm using this jovial example because it's kind of late, but we have to keep thinking about why should anyone care in scientific computing why the computer is on an extra piece of a wire. Nobody in scientific computing cared a jot about the storage area network or a fiber channel LUN or any of that scuzzy remote presentation. So I'll just leave it at that bit, that your application will surprise you that ends up being the truly disruptive piece of CXL.
The software abstraction layer has got to be rock solid.
Correct.
But underneath it, there's a whole orchestrated set of hardware components and other pieces of software working together to make this happen.
Absolutely, yeah, thank you. And I just bring up that story. This baby face complexion doesn't show the deep scar tissue I have building systems at scale for scientific computing.
I'll happily share some of my gray hair with you if you'd like. You know, we can.
I didn't realize that having academic papers available on the World Wide Web was a mission-critical application. We learn something every day.
You haven't been around academics much, have you?
Could you please discuss how applications you have in mind to take advantage of pooled CXL memory will need to use tiering or not? Again, in my black and white world, I'm thinking memory is memory. Who needs tiering at this? But you have different points of view, I'm sure.
Sure. I'm sure everybody has different applications that in mind, but some of the applications that we have been looking at for in the software-defined memory that we talked about, there are multiple reasons why people would use memory expansion. I'm using that generic term rather than just calling pooling, right? One is if you have stranded memory, and you want to make sure that if you start using on pooled memory, then you want to make sure that the work that goes onto that pooled memory can live with it, in the sense that it can live with the extra latency, lower bandwidth that it can provide, any kind of. So definitely we need to understand applications and use cases that can live with that kind of a trade-off.
There's an inherent tiering in CXL
Absolutely.
pool memory because you've got near memory, which is fast, and far memory, which is a tad slower. So
Yes.
that's your first level of tiering.
That is exactly right. So you have to have application, and each application has different requirements. You may see that actually, apart from standard, you'll say that sometimes applications themselves have certain amount of memory that is very crucial to have it high bandwidth, and some of them they can live with having a little bit less bandwidth. We talked about inference. We see that actually in inference
Yes.
use case, something that is extremely close to the accelerators requires to be very at high bandwidth, but out of the total capacity, there is a significant capacity they can live with lower bandwidth. They can live with higher latency. But there is of course, when I say higher or lower, there is a granularity which can be different between applications. So this is what the software needs to hide. And so the point is absolutely valid that as we come to memory, CPU and memory have been extremely closely tied together. So applications are used to having synchronous behavior with memory. So if you try to hide some larger latencies, the software has to be really smart and very aware of what it is doing. And this is where I think the interesting part becomes. To make it completely transparent to the application requires a bunch of work that has to happen. Either it has to happen in the kernel, or it can happen in applications or layers in between. But somebody said it's absolutely right. You can't expect all the applications to change. The world has to figure out how to make it as painless as possible if it has to be successful.
Certainly.
Well, and the hardware has to communicate with the software as well, right?
Oh, yeah.
Again, token hardware guy, I gotta throw in my.
Absolutely.
We've got to have that communication so that hey, what is my device actually capable of? What attributes does it provide?
Yes.
And that's one of the cool things that CXL is providing in the standard in a way that you can rely on it, whether you get that from me or from Steve or Fred or Bob or whoever. So.
Yeah, so I think again, something analogous will happen, except that, again, the challenge is going to have to be more synchronous and coordinated more tightly with memory. But if you watch what happened with the storage area network, it ended up tiering different types of primary storage and secondary storage and things like that. And I see the same thing happening with memory pools. We're going to have different types of memory. Some, I hope we haven't seen the last of storage class memory with Optane. But I definitely see a need to have different types of tiering, some of it being used for data protection, some of it being used as secondary memory to either the HBM or the local DDR type memory. And so the key is to build, and we've started that already at MemVerge with our memory viewer that Charles mentioned earlier, profiling tools that can very precisely profile an application or a process tree and decide what belongs where and place it properly. So I think, so I think that the profiling, the policy engine, and then actually the data mover technology, some of the stuff that, for example, that AMD referred to earlier, are all going to be essential to building this tiering stuff. But I think in general, there's plenty of economic incentive to either get rid of stranded memory or use low-cost memory for less utilized memory areas. So I think there's plenty of economic and also other time to market, time to value, time to insight kinds of benefits that we're going to get from this tiering.
Okay. James, could I ask you to think about this from the HPC point of view? I've not come across CXL mentioned in terms of HPC, but surely it has an aspect.
Yeah, I think everyone, I follow a lot of the HPC community on social media. Everyone's inordinately excited about composable and CXL, and we fill column inches with this. I just want to make a point around scientific computing in general. One of the forefront use cases in high-performance computing, be it oil, gas, discovery, be it genomics, be it life sciences, healthcare. Scientific computing is inherently unpredictable. Einstein famously said if we knew what we were doing, we wouldn't call it research, right? And that really does resonate. And the unpredictable nature of scientific computing and high-performance computing in general means that your computing is always, by definition, the wrong shape for the problem that you are faced with on that particular Tuesday. And the challenges for the systems integrators, the systems analysts, the end user, the scientific computing user, to be able to interface with that computer has been miserable. We've seen a large rise in the US and Europe for a job title called a research software engineer, and that is a specific trained PhD scientist who sits between the algorithm and the computer and the actual publication, and it's becoming an actual job, a profession, if you would. Because of the complexities of interacting with these miserable high-performance computing systems. They are massive, they're expensive, and they are very, very choosy about their friends. If you've ever tried to use InfiniBand or OpenMPI or any of those tools, it's very, very hard and very, very complicated. And to the point where CXL is going to make massive inroads into high-performance computing, to make it transparent and as easy as possible, I cannot go around and reallocate or rewrite every single malloc that I have in my scientific computing workload. It's just never going to happen, and it's just, it's just miserable. So yeah. Sorry.
Can I chime in and ask a question on it, because it's actually, if you look at all our AI ML use cases, the way they are scaling up and scaling out, they start coming pretty close to HPC models that have been, right?
Exactly. Yeah.
So with that in mind, how do you see the kind of a scale requirement this kind of CXL fabric would need in the HPC space?
Yeah, so I can't see a difference between a large, complex reinforcement learning model than when we annotated the wheat genome. The wheat genome was unexpected. It's 10 times larger than humans. So respect your cereal in the morning. That wheat genome is incredibly complicated and very difficult to assemble and understand.
That was an unexpected shade of gray right there.
But we are seeing this annealing of the types of compute that you need for really advanced machine learning, not just a quick word search, but the real machine learning for real. We're seeing machine learning replace a lot of multi-physics codes, which is making a lot of scientists very upset. But the compute that powers both of those is becoming more uniform. So you fix one and you fix two, which I think is good. It's seeing a goodness in the unification of HPC, ML, and AI.
I think the gentleman this morning from Micron called it pliability, right? The idea that we're making systems that can be reconfigured on the fly, and that's one of the things that CXL inherently enables. And Bernie, you don't have to worry if my customers are any indication. There is plenty of high-speed, non-volatile storage class memory coming in the very near future.
Great.
So yeah, no promises. It doesn't have my name on it, unfortunately. But yeah, I would say that's definitely something. Somebody early in the morning, Frank, I think asked about, I think when CMAC was up, about are we going to see SSDs on CXL? And the interesting answer there is, of course not, sort of, kind of, maybe. Right, because again, I can tell you from my experience, pretty much everybody who's doing NAND flash devices is looking at putting them on CXL. But I think one of the really interesting things we're going to see is one device is very likely to present part of its storage as an NVMe and part of its storage as CXL.mem. So feeding into that reconfigurability, that pliability that the Micron guy was talking about this morning, it definitely looks like this audience, right, the Flash Memory Summit people are very much looking at building devices that are going to fit right into that. So, I'm super excited, just even from the hardware side, right? So.
We're already doing that today in MemVerge. We're already tiering between DRAM memory and NVMe SSD. And so we'll just be pivoting right over to CXL when that comes out.
Yeah, well, and the change from block storage, right, to linear. I spent 20-odd years before coming to Synopsys doing storage controllers at LSI, and that was the holy grail for years, whether you called it linear storage or byte addressable storage, or back when the bits on the disk went round and round, that was a pipe dream, right? We got to square storage, and all of a sudden now it's sort of feasible. So I think we're definitely going to see the hardware shifting in ways that make your job easier, so that your systems become easier, so that your damn website will stay up. So that we can solve the wheat genome or whatever's harder.
Better example. And Chris is a proper journalist. Did we answer your questions, sir?
You've answered, you've opened up a whole interesting can of worms. I never knew there were so many different types of worms, which leads me to my personal last question to you all. We've all benefited from memory being memory being memory being memory. Everybody makes the same DRAM. With CXL and memory tiering, are we in danger of losing that and having non-commodity memory in the future?
Oh, are we in danger, or are we in the most exciting time ever of finally seeing some differentiation on that commodity, right? To answer your question, and again, I'll shut up quickly because folks are probably better tuned to this than I am, but the underlying memory chips themselves are not going away, right? I think we heard that all day long, right? But what's exciting about that is where they're getting combined, right? We had was it Samsung and SK Hynix, I think this morning, both showed off some pretty cool modules they were building. There are, I think, going to be so many more degrees of that tiering, right? Your 50 shades of gray. I think we're going to see 50 shades of memory where the system designer is going to get to pick the difference between, is this, non-volatility uber alles? Is this one bandwidth uber alles? Is this one a mix? So I don't think the DRAM chips themselves are going away.
The DRAM chips are going to stay.
DRAM chips are probably going to be
But the
DRAM
stuff
chips.
between them and the
But
applications
yes,
and the rest of the computers.
Going to get so much cooler than we've seen over the last 30 years.
I would echo that. I mean, but one thing that I feel is like, I don't think it's DRAM is not being DRAM anymore, but I think it's getting more precisely defined. What do we mean by memory? What do we mean by DRAM? And that just kind of starts separating out what technology supports it, what interconnect supports it, but actually how the applications, how the software uses it. So I think it gives us a much more flexibility that allows us to build much better systems.
Yeah, the way I see it, you know, people always said data has gravity, and the center of gravity has been storage systems. So I see some of that moving over into memory, a diversified memory pool, and that will accelerate time to value. That will also reduce context switching. I think even help save energy and things like that. So I think there's a variety of reasons to keep things in memory.
Yes.
And that will require a diverse, more than just DRAM to do that economically.
One of the things I've been picking up, one of the little dots I've been picking up, is ESG reporting. I think it's becoming so very influential and important, and will just grow like crazy. And big companies will want suppliers talking to them that can help them lower their energy consumption. It's just going to ripple right throughout the supply chain. And memory, in-memory computing, is so much more energy efficient than sticking it on rotating disk and doing IOs. It just stands to reason. Mr. Panel members, thank you very much for this. 50 Shades of Grey, 100 Shades of Grey, possibly. It's been a really enlightening discussion for me. I'm very grateful to have the opportunity to moderate this panel, and I'd like you please to show your appreciation to them and say thank you very much.